Hi, welcome back to our series, our two-part series on minimalist grammars. I'm your host, Greg Kobola. The previous video went into depth about minimalist grammars, about the structures that we want to be manipulating when we construct expressions, and we introduced operations like move and head movement by means of a semi-worked out example of the English auxiliary system for head movement and raising to subject for movement. Today we're going to finish the extended example by talking about raising to object and passivization. And then we're going to turn to thoughts about the architecture of the system. Right? So this is all up until we're turning to the thoughts about the architecture of the system. This is all an example of how the system works. Once we finish with this example by finishing with raising out to object and passivization, we're going to be in a situation or in a position where I can tell you what I think about what minimalism as a theory actually looks like. So people talk a lot about interfaces and about grammatical architectures, and we're going to be in a position to discuss that a bit once we finish with raising to object and passivization. Okay. All right. So raising to object, very famous kind of construction. We've been studying it for 50 years now. Bill expects John to laugh, and Bill expects that John will laugh. Two sentences, grammatical sentences, many of the same words in them. We say that there's an alternation, that expects participates in an alternation. The first example, expects, is in something like a ditransitive frame. It has an object, a nominal object, John, and it has a clausal object, to laugh. In the second sentence, expects is in what we might call a transitive frame, where it has just one object, which is the clause that John will laugh. Okay? I'm using object in a very loose sense here. There's one argument to expects in two, other than the subject, and it's the clause that John will laugh, whereas in one there are two non-subject arguments to expects, John, and the clause to laugh. So this is the intuition, this is the one intuition you might have when you look at sentence one. Some people have said that what is really going on there is expects has just one argument, one non-subject argument in both cases. In both cases it's clausal, but in case one it's an infinitival clause, John to laugh, and in case two it's a finite clause, that John will laugh. Okay. We're gonna come down on one side of this because it's easier to give an analysis whereby John actually is or becomes an argument of expects than it is in our current setting to give an analysis of one whereby John stays inside the clause to laugh. And we can talk a little bit about why that is. But for now, this is the alternation, and it's incumbent upon anyone, really, to account for the fact that these two sentences are grammatical. And indeed, these two sentences are standing proxy for an infinite number of sentences. We can trivially change the identity of the embedded clauses and the arguments to whatever we want, giving rise to an infinite number of sentences. And there are other verbs like expects that participate in these two constructions. Okay, so these are two sentences that are standing for a vast array of linguistic data. Okay, and we want to account for this. The first thing we can do, and I think this is in general a good strategy, is to just write something down. Okay, so I've heard it attributed to Dijkstra from my advisor at Stabler that, now I can't remember the quote. It's something like this. It's complexity precedes simplicity. Okay, and that I understand that, and I think it was intended in the following way. If you want to get a beautiful result, a beautiful theory, you have to go through slog through swathes of ugly theories first, right? You have to write something down. It's of necessity not going to be beautiful, but it's a starting point. So to get somewhere pretty, you have to start out somewhere ugly. Okay, but you have to start out. Okay, so our ugly position, our ugly starting point, maybe you don't find it ugly, but we're going to change it. Our starting point is this one. So the first frame for sentence 1, we can say that expect selects a clause equals C. It checks the case of something, necessitating that that clause is non-finite, i.e. that it has something inside of it which needs its case checked, i.e. has a minus k feature. And so expect has as its second feature a plus k feature. And then it selects a subject, a D, with its D equals feature. And then it becomes a normal verb, little v. Okay? That lexical entry for expect will allow us to get sentence 1. Okay? And in order for expect to move to the left above the position of the object, of the thing that had its case checked, we're going to have head movement, drag it up the tree. Okay, as it already is going to do. In its other frame, in the other construction, in 2, where it just takes a clause, expect is going to just take a clausal argument with its equals C feature, and then it's going to select for the subject with its D equals feature. Okay. Now again, the equals C feature would allow expect to take a non-finite clause, right? Because we have identified non-finite and finite clauses up to this point in our grammar by giving them both the category C. Okay. This doesn't cause a problem here, because even if we take a non-finite clause in this second version of expect with our equals C feature, we're going to then immediately merge the subject with its D feature, and this subject is going to also have a minus K feature. And then we will have the minus K moving guy inside of the clausal argument of expect, and the minus K newly merged subject. That configuration runs afoul of the SMC, and so if we were to do that, that would be a grammatical dead end. It would never see the light of day. Okay? So we have a little overgeneration in the non-finished grammatical expressions. Okay? And we don't care about this because we only care about the grammatical expressions that we derive as finished ones. Okay? All right, so that's a first approach to this contrast, or to this these two frames that expects can find itself in. So here's an example. So we are using the first frame for expect. We have constructed the non-finite clause to laugh John. If you put your finger over the mother and its left daughter here, the root and its left daughter, i.e. expect, you have that tree for to laugh John, which modulo its C feature is what you would get by constructing to laugh John, right? This is the normal non-finite clause that we know how to construct. Okay, we've now merged expect, canceling out the C feature on to and the equal C feature on the lexicon of expect. And this is what we now have. Okay, the head of this structure is the word expect, and its first feature is plus K. So we're going to do a movement operation. John is embedded in there somewhere as a maximal projection, whose first feature on its head is minus K. Perfect, that's the only one in the tree that has minus K, so movement can apply. And indeed, when we move, John raises up above expect. Okay. In this sense, John has become a derived object of expect. It's in the maximal projection of expect as a direct dependent of expect. However, it wasn't merged with expect. So we might say that a deep object is something that's merged with something else, whereas a derived object is something that is moved to something else. Okay, so John is here a derived object of expect. Next, expect wants to select a subject, and we give it Bill. Okay, and then we do a bunch of head movement. We construct an X. We've skipped over the auxiliaries be and have. Just going to inflect expect. Okay, and then we could add the tense, some tense, maybe a present tense. That would introduce a plus K feature that would then allow Bill to move up and to check off its minus K feature. We would have the sentence, Bill expects John to laugh, which is the sentence that we started with in 1. Okay. All right, so now we've seen that this lexical entry, these lexical entries for expect, give you something like different kinds of object positions. Okay, so we can, and DPs, so in order to, what we've done is we've exploited the fact that we've assigned to DPs 2 features which need to be checked outside of their maximal projection, the D feature and the minus K feature, which means that DPs will have 2 positions that they're going to ultimately pass through. Okay, we might call their D position the position that checks their D feature, their deep position, and their surface position is the one that checks their K feature. Okay, so we can actually use this thing we have set up so far to account for classification. Okay, so alongside 1, Bill expects John to laugh that we just derived, we could also derive 2, John is expected to laugh, the passive version of sentence 1. We've passivized expect. And the object of expect raises to its subject position, becomes a derived subject. Likewise, Bill expects that Mary will laugh. The second frame that expects can occur in can also be passivized, but there we get it as the derived subject. Okay. So what we would like to do is we'd like to account for this alternation, right? This is something that happens in English, and if our goal is to derive the sentences of English, then we have to account for it. We have to explain how these multitudes of sentences are grammatical. Okay, and a natural way to do this is, instead of doing it one by one, we try to find patterns and exploit these patterns so as to cover in one fell swoop as many sentences as possible. Okay, so we already know how to derive sentence 1, Bill expects John to laugh, and we know how to derive sentence 3, Bill expects that Mary will laugh. It would be nice if we could use that machinery that is already in place, those lexical items that are already in place to derive sentences 1 and 3, somehow to derive sentences 2 and 4 and as well. Okay, that's sort of what we would like to do, and by sort of I mean that's what we would like to do. Okay, so let's think a little bit about what the difference is between 1 and 2. Okay, so in 1, or rather in 1, the reason that John is where it is, i.e. in the derived object position of expect, is because expect has a K feature, a plus K feature, that attracts John and that checks the feature of John, right? That's why John is there. Okay. And the reason that Bill is the subject of expects is because Bill was merged with expects. Okay, expects had an equals D feature, and Bill was chosen as the D to check that feature. In 2, neither of those things have happened. That must be the case. Neither of them could have happened, otherwise we wouldn't have had John in the subject position of expect. Okay, John would still be in the object position, and Bill would be in the subject position. But in 2, there is no Bill, right? So there must never have been a equals D feature that checked Bill's D feature, right? Couldn't have been there. And John isn't in the object position of expected anymore. So that plus K feature that moved John to the object position must not have been there either. Okay. So if we look at the bottom of this slide, we see in black, gray, whatever that color is, expect, the original expect that we had that allowed us to derive sentence 1. And in blue, we see what we need to have instead to derive sentence 2. So expected is like expect in that it selects a C, but it's unlike expect in that it doesn't check case and it doesn't select a subject. And instead of constructing a V, it constructs something that needs to be selected by a B auxiliary in order to become a V. So be expected and expect have the similar distribution, and so they should both be V's, but expected by itself is not yet a V. It needs to be combined with a B. Okay? So those lexical items in blue are what we need to derive sentence 2. Okay? Now, this is great, but it seems like there's something going on here. Okay, it seems like there's, if we were to write this down in a big table of our lexical items, we would see again, hey, you know, there's a lot of regularities going on there. We're missing some generalizations. And we could also cash this out in terms of how many lexical items we would need to add to our grammar in order to account for the distribution of intuitively a single raising an object verb. Okay. So we have this decompositional methodology, that allows us to remove regularities or to abstract out regularities by reifying them as new lexical items. Okay. So from expected, we see, okay, well, there's a verb there, expect, that we would like to have common as well in the verb expect that we already have, right? So in both of those, there's a similar verb, and in both of those, they start out with the same feature sequence. They both start out selecting a C, right? Well, let's decompose there. Let's say that equals C, that expect and expected share on the left-hand side of this squiggly arrow. That's because there's a common lexical item there. And let's give that lexical item the name expect. Okay? We have to introduce a new category name. Let's call it Big V. Because it's not quite a little v, but it's still verbal. And anyways, people call this kind of thing a big V. And once we take that out of both of them, in the first one, we see, well, something is left. We still need to get that passive category. And so we need to select a big V for head movement, and have passive. And the particular form of expect that we see in the first lexical item is the passive participle form. So let's name the new head moving lexical item that we extracted from it -en, because the passive participle can sometimes end with en. Not in this case, but sometimes, like in broken. Okay. So from the first verb, we extract an expect, a generic expect, and a passive participle, en. Okay. From the second verb, when we extract our expect, there's a whole bunch of features left over. Right? These are plus kd equals in little v. So they need to go into a second lexical item that's going to combine with this generic expect. It's not going to really impact the pronunciation of any of our verbs. And so I'm just going to give it the name epsilon to signify that it's not going to have much of a phonological effect. But really what I need to do is I need to give it some other name, maybe active voice would be a good name. And just need to indicate that when expect combines with active voice, we don't change the pronunciation. And I indicate that when expect combines with the passive voice, the en, then we get expected. Okay. But I'm going to give these suffixes, these head movers, particular names that indicate what their phonological or morphophonological contribution is, in lieu of writing down morphological equations. Although the morphological equations, in my view, are the fundamental things. Here it's much easier and it fits on this slide. Okay. So let's back up again. I ended up saying a lot, and I forgot whether I made the main point. Here we have these two versions of expect, which occur in these two sentences, sentence 1 and sentence 2. They're both versions of the expect that selects non-finite clauses with an argument in there, noun phrase in there that's wanting to move. But the top expected is the passive version, and the bottom expect is the active version. Okay. Active version of what? Passive version of what? Well, in the original grammar, the original lexical items we had, there was no sense to this question. They were just different lexical items. But after we've decomposed things, there is a common lexical item, namely expect, that selects a clause and becomes a big V. And the difference between the active and the passive, expected and expect, is there's an active morpheme, this silent guy, with features equals V plus KD equals little v. And there's a passive morpheme, a passive lexical item, that top guy dash en, with features equals V and pass. Okay, so now we've reified voice as lexical items. Okay, so let's look at an example here. Expect to laugh, John. This is something that's common to both the sentence Bill expects John to laugh, the active version, and the sentence John is expected to laugh, the passive version. Here we're going to derive the passive version. Okay, but this big VP here is shared by both derivations. Okay, now we can merge our passive head, the en. And notice, by the way, that once we've done that, John is still waiting there to check his case. We merge our B, we skip a couple steps, add tense. Now we have a plus K feature on B. Great, John has been waiting there patiently with his minus K feature. We can move John up and we get the sentence, John is expected to laugh. Okay, so that's great. Moreover, with those lexical entries, we can already derive the form John is expected to laugh and it is expected that John will laugh. Okay. So let's derive it is expected that John will laugh. So we have expect, and it combines with a clause. This time the clause, unbeknownst to it, or moreover, or rather, since we don't make a category distinction between finite and non-finite clauses in our lexicon yet, expect, which wants a clause, can combine either with a non-finite or with a finite clause. Here it's combining with a finite clause, that John will laugh. We add a passive head, add the B, we get B expected that John will laugh. We adjoin it. Notice that we didn't have a minus K feature yet, now we do. And now we keep on going, we add the tense lexical item, B head moves up there, and we have B with an it hanging around, expected that John will laugh. It and the plus K on the head, the tense head, cancel each other out or check each other. We get it moving up to the subject position, and if we scrunch it together so we can see it better on the slide, we have it is expected that John will laugh. Okay? All with the same lexical items that we've used before. Okay. But we still have a different lexical entry for the active version of the finite clause selecting expect. We have equals C, D equals V. Okay? As in contrast to the other expect that we have, which is of category equals C, big V. Okay? This is, again, not ideal. Seems like we're missing a generalization. We could quantify this by measuring how many lexical items we require to add to our lexicon to add intuitively a single verb. But we're not going to do that here. I'm just going to point out, hey, we have 2 expects. It'd be nice if we had 1. How do we get 1 out of these expects? Well, we apply our decompositional methodology. We look at the first expect, compare it with the second expect. We see that they have something in common. They both start with equals C. Okay? And moreover, the second expect is pronounced the same as the first expect. And if we were to decompose the second expect so that we have something of the form equals C and then some new category, well, that would look exactly like our first expect. Okay, we have an equals C and then some category, in this case, big V. So let's decompose our second expect so that actually the first expect is a part of it. Okay? So number 2, expect, that version of expect, we view now as a derived expression, derived from the first version of expect. And how do we turn it into having the feature bundle equals C, D equals V? Well, we add a empty lexical item that combines with it after it takes its clausal complement and adds the features D equals and V. Okay. Now, that element on the right, the silent guy selecting a V and then selecting a D and giving us a little v, looks very similar to this head that I called the counterpart of the active voice back here. Farther back than I thought. Okay. This guy here, that was the thing we had to combine with our generic version of expect in order to allow it to select a, to provide an object position and then select a subject. Okay, it selects a big V, has a plus K feature, a D equals feature, and a little v. And when we look at what we've just taken out of, or what we've just turned our other version of expect into, we see this thing here. Okay, and we can compare those features on that lexical item with the features on this lexical item that we just scrolled back to see. Okay, they look extremely similar. The only difference is that plus K feature that's on this guy that's highlighted but not on the other guy. Okay, that's the only difference between them. So we can decompose again, right? We can say, aha, they both start the same way and they both end the same way. So what we're going to do is we're going to say, well, there is a hidden category there, which I'm going to call agar O. And this agar O is going to take the common suffix D equals V off of both of these lexical items. Okay, there's just going to be one lexical item that has the D equals V feature. Okay, and it's this new one down here. Okay, the difference between these, the other difference between these two, that the one has a plus K and one has a no plus K, that's just going to be a brute difference here. Okay, these two that are sitting on top of each other, oops, this one and this one, are just alternates of each other that both take a big V and turn it into an agar O. This highlighted one does it by also checking the case of something. This lower one does it just directly. Okay. Even though we have added more lexical items than we had before, these are all functional lexical items that in some sense represent constructions. And thus, if we add new lexical items, new open class lexical items to our grammar, to our lexicon, we don't add these. These are not open class. So as we add more lexical items to our grammar, more words to our grammar that behave like expect does, we just add single lexical entries. And these functional projections, these functional heads, will take care of their participation in other constructions. Okay, so here's what our lexicon looks like now. The stuff at the top is just what we had before, the will, s, ud. This is what we discussed in our English auxiliary part of the video. These in the second row, the that, to, and it, this is what we discussed in the raising to subject part of the video, right? That and to construct clauses, that constructs finite clauses, to constructs non-finite clauses, and it we introduced in that same part of the lesson as a way of checking a otherwise stranded plus k feature. We can adjoin it to I didn't add the lexical item that allows it to be adjoined to a v. That's unfortunate. We also have a lexical item that has the features head moving equals v equals expl v, which allows it to be added at the VP level. Okay. This next batch of lexical items here are those that we just talked about. There are passive lexical items and are active lexical items as well. The lower row is the passive lexical items. They take us from a big V to a little v, just by first adding a participial affix un, and then by adding a lexical item b. The top row there, the top highlighted row, takes us again from a big V to a little v, but it does this by definitely adding a d, an equals d feature, and then maybe adding a plus k feature as well. Okay. Our verbs, so these are all closed class expressions. Okay, all these three boxes that we've seen so far, those are closed class expressions. Those are things that we don't expect to need to learn more of. There may be a lot of them here, but they are not open class. They're not going to be new words like them that are added to our vocabulary. Okay, we learn them and they're done. These words down here in these two rows are things that we might conceivably need to learn more of. So laugh is an instance of an intransitive verb. Rain is an instance of a verb that doesn't take any arguments. John is a DP. Seem and expect are raising verbs. Okay, subject and object. And we can have lots of them. The thing that's important here, the thing that's important to note here is that even though we have a bunch of different lexical items in the upper three boxes, they conspire to describe the interactions of various constructions in a perhaps convoluted way, but they do that in a way that allows us to describe the ultimate distribution of words, like laugh, rain, John, seem, and expect, in a very simple way. We've moved the complexity of describing the distribution of words, like laugh, rain, John, seem, and expect, from the words, from the lexical entries for the words themselves, into the closed class part of our lexicon. Okay. All right. Now, I'm going to close the door because it's getting a little loud. All right. Now let's look at normal transitivity. By normal transitivity, I just mean transitivity without clausal objects or anything. Okay? So, what do we do with transitive verbs like praise? John praised Mary. Or Mary praised John. Okay. Well, we have a verb like expect, which is sort of a transitive verb. It has an argument, and then it becomes a big V. Okay? It's just that its argument is a clause. Well, let's try the same game, but with an argument being a DP, like praise's argument, John. Okay? Maybe praise selects a D and becomes a big V. Once we have a big V, we can do all of our passive and active lexical items to it. We can use our lexical items for passive and active on that thing. Once we have a big V, it fits into the grammatical pipeline. Okay, so here's an idea for how to treat praise. All right, we can build a big VP, praise John, and it looks as it does on this slide. Okay, we can start pursuing the path towards activity by adding a lexical item that checks case, that equals v plus k aggro lexical item. Okay, so it combines with praise, triggering head movement. We see that the head of this entire structure has its first feature plus k, and inside of this structure there's John, which is a maximal projection, whose head itself has the matching feature minus k as its first feature. So we can move them. We can continue on with our active group of lexical items, adding a lexical item equals agar 0, d equals v, which combines with an agar o phrase to construct ultimately a little vp once we've added a dp. Okay, praise continues head moving. All right. And then we can just continue on. We can add our subject, Mary, and we end up with the sentence, Mary will praise John. All right, now we had two versions of agar o. Right? We had an agar o that checked case, and we had an agar o that didn't check case. Okay, we've seen, or I hope you agree, or you are willing to believe, that the partial derivation that I showed you could be extended to a full derivation of the sentence, Mary will praise John, or Mary praises John. Okay, but we used the agar o that checks case, and they have the same selection properties. They both select a big V. That is a big V. Praise John is a big V. So we could have used the other one as well. What would happen then? Okay. Here we used the other one. Didn't check the case, but, because we didn't check the case, now when we merge a DP, like Bill, we have two things in our structure that both want to move for the same reason, which is disallowed by the SMC. Okay, so our grammar permits us, or the lexical items we have allow for us to start building a sentence that isn't going to work, but that's okay. Okay, our goal is not to have a grammar that allows us to extend every derivation into grammaticality. There are some people that want that. Right, that's, I think, sometimes called not having look ahead. But I don't care about that right now. I want our grammar to just satisfy the property of being able to correctly derive all the grammatical sentences and not deriving the sentences that we don't want to derive. I don't care what it does along the way. As long as it associates the correct meanings with the correct sentences, I'm happy. Okay, until we have that, I'm not so excited or impassioned about these other constraints that we might impose. Okay, so even though we have two choices for agar o, only one will work, and the other one, it's okay if we pick it because it won't allow us to generate anything ungrammatical. Okay, so let's think about what else there is. Because now we are able to derive raising to subject verbs, verbs that alternate between taking finite complements and having an it as their subject, and taking non-finite complements and then raising the DP out from that non-finite complement to become their subjects. We have verbs that do the same thing, but with respect to their object position. But there's more under the sun than that. There are some verbs that allow for raising to object, but that don't alternate. They have the frame verb John to laugh, but they don't have the frame verb that John will laugh. Okay? Here's an example. Bill caused John to laugh, but not Bill caused that John laughed. Okay, what do we do there? Well, in order to implement or in order to describe verbs like these, which make a distinction between finite and non-finite clauses, it's helpful to reintroduce a distinction between finite and non-finite clauses. Right? Previously, it turned out that we didn't need to make a distinction, categorical distinction between finite and non-finite clauses. But now it seems we just hadn't looked at enough data. Here is where we need to do it. We didn't need to do it before. So it's good we didn't need to do it. It's good we didn't do something we didn't need to do before, because now we see, aha, this is where we need to do it. Okay? We could have thrown the kitchen sink at everything before. But by not doing that, we've discovered this kind of construction is what pushes us to making or what forces us to make a distinction between finite and non-finite clauses at the grammatical level. Okay? So let's do that. Now 2 is not going to be a C, or it's not going to produce a C, it's going to produce an I. It's going to go back to producing an I. Oh wait, you think everything we've done before has been predicated on 2 producing a C. That's okay, we'll get it back. Okay, so now cause is going to select an I, a non-finite complement, and 2 is the kind of thing that produces that. Okay, and why can't cause combine with the finite complement? Well, because it doesn't select for C's, it selects for I's. Okay, but previously we've seen that we can get away with a lot, we can explain a lot, account for a lot, if things, especially about, we can account for a lot about alternation patterns between verbs that select finite and non-finite complements. If we say that there's a relation between non-finite and finite complements, namely that non-finite complements are the same category as finite complements. Okay? That, in other words, the words on the slide here, that I, the category I, is a kind of C. Okay? And we've seen before we can implement these is-a relationships between categories, these partial orderings over categories, via lexical items. It's not obvious to me that that's the right way to do it in any sense of right. It's not obvious to me either what that means, or even that it's the best way of doing it, right? One approach is to simply say, we have categories, and these categories have somehow a partial ordering relationship between them, and when you say, I want to select for this kind of category, you're also willing to select for anything that is ordered below that, right? That's a possibility, an alternative implementation of this. Raffaella Bernardi and Anna Sabolci have a nice paper about partially ordered categories, where they discuss exactly this alternative. But here we didn't do that, we instead implemented this partial order relation via mechanisms that already existed in our grammar, like merge. Okay, we do it by adding a lexical item like this, a lexical item, empty lexical item here that says, give me any I, and I will produce a C. Okay. So from this lexical item, we can continue to use non-finite clauses as finite, as a particular kind of finite clause. Or in other words, this suggests that we have a category clause, which is C, and we have a subcategory of clauses which are non-finite. Okay, and cause, the verb cause, just selects for that subcategory, whereas the other verbs that we've seen just select for clauses in general. Okay, some other things that happen. Some verbs only appear in the passive, right? Like rumor. It's rumored that John laughed. John is rumored to have laughed, but no, Bill rumors that John laughed. Okay? This fact, the existence of verbs like this, was counted as an argument against incarnations of transformational grammar, which viewed all passive constructions as derived from underlying active constructions. And it was said, hey, that doesn't work because look, you have passive constructions that are grammatical with no grammatical active variant to derive them from. Okay? And no Bill rumors John to have laughed either. Okay, so there's no active version of rumor here that we can fall back on to derive the passive version from. Okay? But note that we aren't deriving a passive version from an active version, or an active version from a passive version. What we're doing instead is we're deriving both versions from something else. They both, active and passive, have something in common, and then they branch off in different directions. Okay? So we could just assign a verb like rumored a category that puts it on the passive branch already, on the passive part of this grammatical branching. We could assign it the category equals C pass, which makes it already in the passive world. It can't become an active, okay, but it can still select a complement clause. Okay. Alternatively, we could say no, rumor is exactly like expected on the syntax, but for some weird reason, unbeknownst to us, there's no explanation of it, it's just how the world is. If rumor combines with an ag or o lexical item, somehow that's just not morphologically realizable. We just can't pronounce it. We can build it, but we can't pronounce it. Okay? That works. And we could also view this as just a pure matter of frequency. We can say, yes, rumor is 3 and 4 are perfectly grammatical. The system derives them. It's just that they are so infrequent. They're vanishingly infrequent, and what we know is, and we assume that our judgments of acceptability reflect frequency to some extent, and because this is so infrequent, we just judge it as ungrammatical. Okay. This last option requires a whole lot of heavy lifting, right? There's a lot of promises implicit there, right? We need to somehow make a link between unacceptability and acceptability and frequency and infrequency. Okay, and it's not obvious how to do that. That's a very difficult problem. Shalom Lapham has been working on this, and I think with Alexander Clark. This is a difficult problem. They have some success. It's not a linear relationship between frequency and acceptability, but there is, it appears, some relationship between frequency and acceptability judgments. Okay, so it's not necessarily impossible, but there is a lot that needs to be worked out if we want to go that route. Okay, I personally find the first two options the nicest. I sort of like the first option, just saying syntactically rumored. It's already on the branch towards passivism. On the other hand, it might be nice if we were to treat rumored itself as being derived from something like a more basic form rumor, in which case maybe it wouldn't be as nice, it wouldn't fit as nice into this system if we have to have a lexical item that just takes rumor and turns it directly into a passive phrase. Maybe we would do better by pushing this off into the morphology. On the other hand, in the morphology, the second bullet point, or I guess the third bullet point on the page, but the second bullet point discussing possible options of analysis, in the morphology, we have no theory of why this would be, and so it's all just brute stipulation. Okay, so I think the argument against transformational approaches to grammar based on obligatory passive verbs doesn't have its once decisive force, or perhaps decisive force, but it is still something that we need to worry about, right? There is something there that we need to discuss. Okay, it's not obvious to me if there's anyone that does much better, but it is an observation about an interesting fact, and everyone that's trying to analyze English needs to be able to account for this fact somehow. Okay. There might be more options other than the ones I've listed here, right? But these are just some that I thought of off the top of my head. Okay, now, what is interesting is when a theory can't account for any logically possible data, right? If your theory could account for anything, then the fact that it does account for what you see is perhaps not so surprising, right? You might feel that your theory is just over-engineered. You've overfit the data, right? It could have accounted for anything, and so your theory isn't really telling you much about the world, right? You just have an overpowerful theory, and yeah, well, you use it to fit this data. Good job. Okay, so it's interesting to consider what could exist that your theory wouldn't be able to describe. Okay, so one thing, there are many things that this approach to grammar even can't describe. So it's mildly context sensitive, or better yet, equivalent to multiple context-free languages, or is only able to describe multiple context-free languages, which means that there's a whole swath of patterns that couldn't even be described by any set of lexical items at all. Okay, but this particular analysis, the lexical items that we have now, it wouldn't allow us to describe the following kind of alternation in a nice way. Okay, so a sentential complement taking verb, right? So it's going to take something like a C or an I, which is passivizable. So the verb itself is passivizable. It takes only a that complement in the active, but takes either a that complement or a to complement in the passive. Okay. So why wouldn't we be able to describe this well? Well, because in order to take a complement structure, in order to take a complement, you want to have an equals something feature. If you take only a that complement, well, we don't have a way of describing only that complements, but we can approximate it. So in the active, if it only takes a that complement, then that means that there can't be something moving inside of it. Okay, so maybe that verb itself will have to take a directly select for a D, right? But then it wouldn't be passivizable. That's tough. But the fact that it also can alternate between that complement and a to complement in the passive, it's just a whole bunch of limitations that don't fit naturally together with the system that we've developed so far. Okay, let's give you an example, like think. So Bill thinks that John is laughing. That's an active use of think. It takes it that complement. Bill thinks John to be laughing. I put a star there. In the passive, however, it's passivizable, right? Requirement 1. We have it taking a that complement, but we also have it taking a to complement. So it is thought that John is laughing and John is thought to be laughing. Both of those are fine. This is awkward, okay? But, of course there's a but, it's not obvious that this is not, it's not obvious that the star I put on the sentences in 2 is indicating that we want to rule it out as ungrammatical, that we don't want to be able to generate it, because there are sentences or phrases like think me to be, which are relatively frequent. So I did a Google search just before making this video, and you have over 1 million hits. I must warn you, the first couple of hits are look to me like questions by translators or questions by second language learners of English, but there are a robust number of actual uses of think me to be, often in older books. So here's a sentence that uses this. It would hurt even my delicacy, little as you may think me to possess. Okay, this isn't think me to be, this is think me to possess, which is even more infrequent because think me to possess occurs less frequently than think me to be. But this sounds great. And in fact, a great deal of sentences that are like think me to be sound wonderful, or think you to be, or think him to be. They sound pretty good with pronouns, but not with full DPs. And I don't know why that is. Pronouns seem to behave differently than full DPs in psycholinguistic theories like the dependency locality theory of Gibson. At any rate, if we treat pronouns as the same category syntactically as DPs, in order to get these sentences here, the think me to be sentences, we're going to have to be able to derive an active to complement selecting version of think. Okay, which means that it is not actually a problem for us here. Okay, it's sort of a problem because Bill thinks John to be laughing doesn't sound so good, right? There's something going wrong here. And so someone needs to step up and account for what's going wrong there, whether it is in fact ungrammatical, i.e. we don't want to derive it, or whether we can account for its deviance in some other way. Right? But since we have sentences like to there that are fine, it seems at the moment, maybe as a heuristic, we should allow to be derived and hope that some other extra grammatical factor or other grammatical factor can rule it out. Okay, but here's another alternation that so there's not going to be any big reveal. I'm just honestly not sure how to deal with this at all. Okay, so you have things like I made him laugh. So make doesn't select it selects a new kind of complement for us, right? We might think that it's selecting a little VP. So I made him laugh. I made him praise her, right? It seems like it's selecting for a verbal unit. Okay. Also, we can't you can't get that many. You can't get tensed items in there. So I made him have eaten his dinner, not a tensed item, but it's not clear that that's good. I made him be praising Mary. Sounds sort of weird. Certainly not I made him must praise Mary, or I made him will praise Mary, right? I made him laugh. In the passive, however, you have he was made to laugh. Okay, suddenly you have a to. Okay. But not he was made laugh. Maybe that is okay. He was made laugh. Doesn't sound as bad as I made him to laugh. At any rate, there's a different kind of complement that seems to be selected in one as in two. And of course, we can't have a finite clause complement. I made that he laughed, right? Or it was made that he laughed. Okay, so in the active, here for, it looks like make should have features something along the lines of equals little v, big V. Whereas in the passive, it needs to have features something along the line of equals non-finite complement passive. Okay. So we can account for this, but it's not obvious how to unify these two separate lexical entries here. Right. So that's an interesting puzzle. If anyone figures out how to deal with that, I'd love to know. Okay. So now we've finished up our discussion of how to use this formalism to describe linguistic data. Okay. And now what I'd like to do is to talk about some of the formal features of the formalism, not in what I might normally mean when I say formal features of the formalism in the sense of its generative capacity, but I want to talk about perhaps more philosophical formal features of the formalism. I want to talk about the role that derivations play, and I want to talk about exactly how the formalism is working. Okay, we've seen it work, we've used it, but I want to reflect on exactly what's going on. Okay, and here derivations play a fundamental role. Okay, so I want to take a step back and think about the big picture here. Okay, the picture that we work with looks something like, as in this picture. This is the grammatical architecture that we're assuming. Syntax here is supposed to glue together form and meaning. So we have this blue circle syntax and arrows pointing out from it, this pi labeled arrow pointing to form, and this lambda labeled arrow pointing to meaning. And this is to be understood as syntax does something, produces some structure maybe, and pi, the interface pi, interprets it as a form, and the interface lambda interprets it as a meaning. This is the sort of picture that you see in transformational settings. Okay? It's also the picture you see in categorical settings or in tree adjoining settings, right? This is a very common big picture. Some people criticize this picture as being syntacticocentric, but I think therefore that this picture is not at all reflective of anything deep. It's just a matter of personal choice. I think that that's not quite right. So the goal that one is trying to achieve by writing a grammar formalism, one immediate goal is to specify the form-meaning pairs that are licensed by the grammar, right? Which forms have which meanings? That the sentence, "Hi, my name is Greg," means what it does and not, "Oh, gee, I'm super hungry." That's what we're trying to specify. We're trying to specify which forms can have which meanings, okay? So that's a pair of forms and meanings, right? From a categorical perspective, from category theory, we would specify that those form-meaning pairings using a diagram like this one. Okay, there's some pairing of forms and meanings. Pi 1 interprets this pairing of form and meanings as the pair, as the form, a part of the pair, and pi 2 interprets it as the meaning part of the pair. Right? This is what you would get if you read a book on category theory. Okay? And of course, that's exactly the same picture here. We just named things differently. Okay. So what am I saying? I'm not saying linguistics is category theory. I'm just saying that if you're trying to specify form-meaning pairs, you're going to need a picture like this one. At some level, there will be some way of analyzing what you're doing such that this picture is true of what you're doing. Okay? No matter who you are, no matter what you're doing, this is going to be somehow embedded in what you're doing. Okay. But that thing, that blue circle that I was calling syntax, has been fleshed out in different ways, right? So back in the days of government and binding theory, the blue circle called syntax actually looked like this. There were 4 levels, perhaps more. You had a level of, and they were related to each other in a certain way. You had deep structure, and you did things, and then you had surface structure, and you could do things in various ways, obtaining phonetic form and logical form, PF and LF. This was all in the world of syntax still. And in order to get the form associated with a structure, you interpreted its PF representation. And in order to get the meaning associated with the structure, you interpreted its LF representation. Okay. In minimalism, people often talk about it in the following way. You have some derivation, that's this squiggly line. It's happening and it's constructing trees. And then you interpret those trees as forms and as meanings, okay, by means of different interface maps. Okay. Of course, you could also reify derivation. So we've been, maybe we haven't been, we can draw derivation trees and say, okay, derivation trees are interpreted as trees, and then those trees get mapped to forms and meanings. Right? So instead of having a squiggly magic line that represents the process of derivations, we could reify derivations as things and then interpret them as trees by carrying out what were the instructions that the derivation qua tree records. Okay. So what are derivations reified? Well, a possible derivation is either a lexical item, right? And so a derivation here, a derivation tree, is a representation of steps you should take to construct something, of steps you could take. Okay, so if I have a lexical item as my derivation tree, that is a representation of the instruction, take this lexical item out of the lexicon. Okay. If you have constructed two things, if you have a representation of the derivation of two things, then you might want to say, okay, the next step is to merge them together. That's represented as this derivation tree here on the right. You take the two subderivations you've just created and you write merge on top of them. Okay, that's a tree, a derivation tree, and it represents the instructions that say construct T1 and construct T2 and then merge them together. Likewise, if you have a derivation tree, which is an instruction as to how to create something, and you want to apply the move operation to it, you want to move something around in it, well, we represent that by this derivation tree. And that says construct T as according to the instructions that T gives you, and then apply movement to the result. Okay. Those are the three things that you can do in minimalism. You can take a lexical item, you can merge two things together, or you can apply movement. And accordingly, if we want to have a derivation tree, a way of describing steps you could take, those are the steps you can take. Okay. So, how do we go from derivation to trees? Well, by doing what the derivation tells you to do. Okay. So where it says merge, you merge, and where it says move, you move, and where it says lexical item, you grab a lexical item out of the lexicon. Okay. So this diagram here, this picture of the way syntax or the way grammar is supposed to work is perfectly clear. You have derivation trees, and we've just seen what those are. They're trees of instructions. And you can turn them into the normal syntactic trees you know and love by doing what the derivation tree tells you to do. Okay, this is a very clear picture that allows us to understand this weird picture here. It's not clear what this is supposed to be with this squiggly line that says derivation, but it's very clear what this is. Okay. Now, not every possible derivation is well formed, right? The derivation tree just says, hey, carry out these instructions, but it doesn't somehow, it's not required that those instructions make any sense, right? I can tell you to merge two pieces of chalk together, but it's not going to work. You might say, well, that won't work because pieces of chalk aren't lexical items. And that's also a reasonable objection. But even if we restrict our attention to actual legitimate derivation trees, still there are some sequences of instructions that are not possible to carry out. Here's an example. This derivation tree, move, move, John, is telling us from the bottom up, grab John out of a lexicon, apply the movement operation to it, and then do it again. But you can't do that. You can't apply move to the lexical item John because you're not allowed to apply move to lexical items in the first place. You can only apply the move operation if you have a non-trivial structure, the head of which starts with a plus feature that itself contains somewhere inside of it another leaf, which is the head of a phrase, and this leaf's first feature is the corresponding minus feature. John, as a recipe for taking the lexical item John out of the lexicon, does not meet this condition. So this is a description of a sequence of steps that you can't actually carry out. Okay. So how do you determine if a derivation is well formed? Right? Is it just you try it out, and if it works, then it works, and if it doesn't, then it doesn't? Well, another way of asking this question is there structure to the notion of well-formedness? Does being a well-formed derivation, is that a property that has a structure to it, or do we just have to determine it in an ad hoc way? Okay, let's take a step back, or a step in, maybe, I'm not quite sure what the right metaphor is, and go back to real-life linguistics. So Hagit Borer has a theory called exoskeletalism, and my understanding of it, my weak sauce understanding of it is that syntax applies willy-nilly, and the interface maps filter bad stuff out. Okay? So this is a cool idea. I think it's not just Hegel Borer that has this idea. I think a lot of people have this idea. But what's really at issue here? Okay? Right, how would we decide if this is the right idea or not? Okay? And so I think a relevant question is, how hard is it to delimit bad derivations from good derivations? Okay? If it's actually super hard to distinguish between bad and good derivations, then this idea is going to make the interface maps do a lot of heavy lifting. Okay? If on the other hand it's super easy, then maybe this is great because the interface maps don't have to do much extra work. Okay? So let's figure out how to check a derivation to see whether it's grammatical, whether it represents a sequence of steps, the carrying out of which will result in a well-formed, complete expression. Okay? So we're going to see now what information we need to have in order to determine whether a possible derivation tree is actually well-formed or not. Okay? So there are three cases for a node of what a node in a possible derivation tree can be. It could either be a lexical item, it can be a node labeled merge, or it can be a node labeled move. Okay? Now what we're going to do is we're going to start at the leaves and walk up the tree, and we're going to be checking to see if the derivation is well formed as we go up. Okay? So let's, one by one case by one case by case, figure out what we need to do to verify that a node with that label, as a lexical item, merge, or move, actually corresponds to a well-formed derivation tree, i.e. a derivation tree that is a description of an actual convergent derivation. Okay, so if you have a derivation tree of the form L, a leaf, a lexical item, you need to know what L is. So you check if it's in the lexicon. Okay? But the lexicon is a finite amount of information. It's just a finite set. So all you need to do to see if a leaf is a valid derivation tree is you just look to see if it's in the lexicon, which you can do. So that's the easiest case. What about merge? Okay, so when is a derivation tree whose root is labeled merge? When is that okay? Well, we know that derivation trees whose roots are labeled merge, or really any node is labeled merge, that node has to have two daughters, because that's just how we defined derivation trees. A node labeled merge always has two daughters, and a node labeled move always has one daughter, and a node labeled with some lexical item has no daughters. So merge has two daughters here. So let's assume that both of its two daughters are well-formed derivation trees. If either of them isn't, then neither is merging of that. Once you have constructed an ill-formed, a not possible to carry out derivation, then there's nothing you can do to fix it. Okay? So, we have two well-formed subderivations, T1 and T2. How do we know if merge of T1, T2 is also a well-formed derivation? Well, you need to know the first features of the heads of each of these, of the trees that each of these derivations derive. So you can check to see whether they're the right kind, right? You have to have an x equals or equals x and a y. And whether they match, right? If you have an equals x and a y, that's not going to work. If you have an equals y and an x, that's not going to work. Even though they're the right kinds of features, you have to have an equals x and an x, or an equals y and a y. Okay? And you need to continue to remember the next feature of the head of the first argument to merge, in case it's the argument to a later merge step. Okay? In general, you need to remember the features of the head of the expression that you're deriving. Okay? If you know the features of the head of the expression you're deriving, then you can check to see whether or not a derivation tree whose root is labeled merge and whose two daughters are labeled T1 and T2 are labeled T1 and T2, you can tell whether that is well formed just by remembering the features of the head of the expressions you're deriving. Okay, what about move? Well, given that some derivation tree is well formed, what about popping a move on top of it? Is that well formed? Well, you need to know what the first feature of the head is, and you need to know the first features of the moving expressions, right? You need to know this for two reasons. One, so you know whether there is someone that can move at all. If there isn't anyone that can move, anyone that has the matching first feature as the first feature of the head, then you can't apply move. There's no one to move. But you also need to know if there's too many. Because if there are too many movers, potential movers, then you break the SMC. The SMC says this is not a derivation which is allowed to continue. You can't apply move here. Okay. And you need to continue to remember the next features of the head and the next features of the head of whoever moved, in addition to the other moving features. Okay. So in general, you need to remember the feature bundle of the head and the feature bundles of all moving expressions. If you have that information, if you're remembering that information, then you can check to see if move is well formed, you can check to see if merge is well formed, and you can check to see if the lexical items are well formed. Okay? Let's see how this works. So this is a super simple lexicon. It only derives the one sentence, every boy will laugh. And here is a derivation. There are actually two of them. I'm going to keep the one on the left the same. I'm not going to change it at all. And then we're going to go through the copy on the right from the bottom to the top without actually doing the derivation steps we're supposed to do. We just want to make sure that it's a well-formed derivation. Okay? So we're going to start by checking that each of the lexical items there are actual, each of the leaves there are actually lexical items. And they are. And we're just going to remember their features. Okay? So those are the features of those lexical items. Okay? And now we're going to walk up the tree. What we can do, there's a merge node, the very bottom one, that immediately dominates two things, the features of which we know. We can look, we see the first feature on the head of each of them are the appropriate shape and they match, they have the appropriate name. So we can, in fact, carry out that merge step. We're not going to, but we know if we were to carry out the merge step, the resulting expression would have at its head the features d and minus k, because we would check the features equals n and n. Okay. Now, the next merge step, its left daughter has head features d equals v, and its right daughter has head features d minus k. We check, do they match? Yes, we have a d equals and a d. Great, we can put them together. But when we put them together, the d features are going to go away. The d equals and the d are going to be checked. The only feature on the head is going to be v, but there's still going to be one feature on the head of the second argument, minus k. It's just going to be floating around there. We're going to need to remember it too. So I'm going to separate features on non-heads from the features on the heads with a semicolon. So here this says the feature on the head of the expression is going to be v, and the features that are in the other expression that are distributed throughout the expression as potential movers are after the semicolon, and here it's just minus k. Okay. The next thing we can check is to see whether or not the merger of the will lexical item and the rest of this stuff is going to be grammatical. Well, we check to see that the first features on the heads match. They do. So we can put them together. We check the equals v and the v features. And we remember the presence of this guy that has a minus k feature. Okay. Now we would like to perform a move step. We want to make sure that the first feature of the head is a plus feature. It is. We want to look at the features of all of the moving things, all the potential movers. There is one. It has minus k. That's good. We check to see that there aren't any additional ones that have minus k. Nope, that's the only one. So in fact, we can apply movement here. And what we end up with is what we would end up with is an expression of type S, whose only feature is S. Okay? So we know not only that this derivation here, on the left here, or the only one that's there, corresponds to a valid sequence of steps, but we also know that if we carry them out, we'll end up with an expression, a complete expression of category S. Okay, we didn't carry out this derivation. We just checked to make sure that it was going to be well formed. Okay, as a process of making sure that it's well formed, we learned about the syntactic type of all of the intermediate expressions that we would build. Okay, so it's actually very easy to do this. So this simple bottom-up procedure, we only have to remember a finite amount of information. It corresponds to a number of models of grammar from computer science that we know about. It corresponds to a finite state tree automaton. The well-formed derivation trees make up a regular tree language. We can write a formula in monadic second-order logic which exactly describes the well-formed derivation trees, etc., etc. Right, there's a lot of different ways of doing this. It is a well-behaved property. The property of being a correct derivation, a well-formed derivation, is a robust property with a rich structure that we can take advantage of. Okay. What it depends on, however, is there being a finite upper bound on the number of unchecked features in any expression. Okay. And the shortest move, the SMC, is really the constraint that's contributing to this. If we abandon the SMC, then we no longer have an easy way to check well-formedness. Or rather, this way of checking well-formedness might still work, but it's going to be much more complicated. Okay, now let's go back to Borel. Remember, Borel was suggesting we have a free, wild, uncontrolled syntactic process that then the junk then gets filtered out at the interfaces. Okay, now I want to state a theorem that isn't due to Borel, but it's just in the folklore. If you have a regular set of trees, like the set of well-formed derivation trees, and a partial regular interface map F, regular is being used here with a precise technical content, but we can think of it as simple, then the set of derivation trees, the set of well-formed trees that F is defined on, can be given directly as a sublanguage of the original regular tree language. In other words, we can write a grammar that directly generates only those derivation trees that can be successfully interpreted at the interfaces. Right. But also, the interface maps restricted to just those derivation trees in this tree set is also a regular interface map. Okay, so in other words, we could have as input all of the derivations, even the ill-formed ones, and we just restrict our interface maps so they're only defined on the well-formed ones, and we don't add any complexity to our interface maps. We add some complexity, but we don't change the category of complexity. Okay? So what this is telling us is that if our derivations are structured in a simple way, and our interface maps are structured in a simple way, then we can shift the work around about who is checking for grammaticality of the derivations. You could either just give it all to the interface maps to do, or you could take it all into the derivations, and they're going to check not only that they are syntactically well formed, but also that the interface maps are going to not find them interfacedly ill-formed. Okay? So Borer's idea, as I described it, she has more ideas than just that, is that we can shift the work around. Okay, let's shift the work around, let's put it all on the interfaces. Okay, so we know we can do this. That's what this theorem tells us. So there's no empirical content to this idea. Okay, but there is something that we might call theoretical content, which is the question about what is the optimal arrangement of work. Okay, so given that we can shift the burden around of checking for well-formedness. We can say some well-formedness is grammatical, some of it is semantic, some of it is, phonological, morphological. As long as those well-formedness conditions are regular, we can lump them all together, we can divide them up in any way we want, we can push the responsibility of checking for well-formedness of any kind to anyone we want, or divide it up in any way we want, and it will still get the same answer. Okay, so we might want to know, what is the optimal arrangement of word? Okay, it's not obvious what that is. Here's another thing that's totally unrelated to what I just said, but it's something that we discussed earlier on in this video, not in this video, but in the previous video. We talked about feature percolation as a way of dealing with the dependency between the choice of subject and the choice of clause in a raising construction. So on the top layer we have the lexical items that are for the sentence, "It will seem that John laughed." And on the bottom in this first box we have the lexical items that would be used in the sentence, "John will seem to have laughed." Okay. Here there's no movement. We just record the dependency between the choice of subject and the choice of clause by duplicating lexical items and adding information to features. So seem prime, that selects a finite clause, is not a V, but it's a V that has selected a finite clause. And all of our auxiliaries need to continue to record this information. I'm not a B, I am a B that has selected a finite clause selector. Okay, and likewise with this version of will, I'm not, or rather, I want to select a finite clause selector, and then I want to select an expletive DP. Okay, this was a way we discussed about how we can enforce the dependency between it and that, or between no it and to. Okay. And movement was a way that we could do that without increasing our categories, without duplicating our lexical items. Okay. But now that we have this notion of how to check the well-formedness of a derivation by recording the syntactic information, the syntactic type of an expression, the feature bundles of everything, we can actually see what we might think of as feature percolation re-emerging in terms of the information about syntactic feature bundles that we can use to check to see whether derivation is well formed. So in John seemed to laugh, if we just look at the complement clause to laugh John, right, which seems selects, its featural content is C, that's the category of seem, and it has a -k expression in it somewhere. Whereas the featural content of the finite clause, that John laughed, is just C. Okay, so this -k on the first is something like feature percolation. We have a C, and then we also record, oh, and there's a -k in there too. Okay, so movement implements feature percolation, but it pushes the mechanisms for feature percolation away from the actual features that are being selected for and into the derivational well-formedness check. Okay, so this C -k, well, it's sort of a bad example here. If once seems selects this, once seem selects either of these, in the first case, seem to laugh John, it will be of category V, semicolon -k, and seem that John laughed will just be of category V. If we compare that with seem prime and seem above, what there I was calling V superscript C is here derivationally V semicolon -k, and what I was calling V is here V. Okay, so the actual feature percolation is pushed into the derivational process. This is neither good nor bad, it's just explaining that this feature percolation strategy isn't an alternative to movement, it's the same idea as movement. Movement just implements it differently. Okay? So what I would like to draw from this as a moral is that understanding proposals in terms of derivational structure is informative. Okay? And I want to make this point because I find that it's one that people sometimes object to. Even though I say we could reify derivations, it's by drawing them as trees, that's just a way of talking about it. We don't need to reify derivations. We don't need to say that something is constructing these derivations or that derivations are real objects out there. We can still think of them as processes. But by looking at them in terms of trees, we're better able to visualize the structure inherent in these processes. We're not adding structure to the process. That structure is already there. By drawing it as a tree, it just allows us feeble humans to visualize that structure better. Okay? It doesn't matter if we say these are real or these are not real, because that same structure is going to be there. And it's still going to be true that movement is a form of derivational feature percolation, regardless of whether or not you want to reify derivations. If you don't, if you think that derivations are just processes, that same information is being kept track of. The process is keeping track of the fact that seemed to laugh John is a V that has extra a minus K guy floating around. Okay? So let's go back to architecture. People talk about multiple spell out, and I think we can represent it as sort of this picture, right? If you don't know what multiple spell out is, probably this picture isn't going to help you. Let me say 10 seconds what it is. Multiple spell out is the idea that as you're running your derivation, you are spelling out, you're interpreting parts of it that you've already built up as you're building up the rest. Okay, so you interpret the derivation multiple times, not over and over again in the same spot, but as you're building things, the things you've already built are being interpreted as meanings and forms, and then somehow you're putting them together. Okay. All right, so this is that's something that people talk about. It's never really clear exactly how they're assembled, right? How the parts that you interpret get put together how the different parts that you've interpreted differently get put together. Like, no one is really specific about that, but it doesn't matter because we can interpret that as what we've been doing. Okay. This is the picture that I want to be suggesting here. We have a derivational process, and we're not using it to build a tree. We're just directly interpreting it as a form or a meaning. Right? I think that this is really sort of what people mean when they talk about multiple spell out. Okay? They have that derivational process that's being interpreted as we carry it out as forms and meanings. Here's, I think, another way of looking at it that is easier to understand. The derivation is interpreted as a form and as a meaning. Okay. Now, so I'm viewing the bottom thing as a description of multiple spell out, and I'm viewing the top thing as a description of, sort of like not multiple spell out, sort of the more traditional PF-LF perspective. Okay? Who is right? Actually, so you could think of those pictures as related to multiple spell out on the one hand and a more traditional but minimalized version of the GB interface perspective, right? Here's what we have. And we can ask, who is right? Okay. Normally it's a hard question, but here it's easy because derivations are isomorphic to derived structures. Okay. This is not normally the case because there's no point to transform something into itself. Okay, so I've made a couple of promises. I've said that syntax glues together form and meaning. Okay, here's this picture I made. By the way, when I say who's right, and normally this is a hard question, but here it's easy, what I'm saying is this bottom thing is right. Or perhaps a more careful way of saying it is they're equivalent. Okay, so I've said syntax glues together form and meaning. We have syntax, we ship it off to form, and we ship it off to meaning. But, I mean, I can say things all I want. That doesn't make them true, to my great chagrin. In order to keep these promises, in order to make good on my promises, I need to tell you what these interface maps are actually doing. Okay? Well, that looks ugly. Interface objects are sequences of strings. Okay? We have the head, the stuff in the maximal projection that's not moving, and we have a bunch of independent moving pieces. Okay? Jens Michaelis proved this in his dissertation, that this was a way of interpreting minimalist derivations. Henk Hakema proved something similar in one direction in his dissertation a little bit later. Okay. So how does this work? What is the idea? The idea is that you only need to keep track of which strings have reached their final position, but not of their internal structure. Okay. In order to interpret a derivation at the interface, we can go bottom up and we can spell out structure as we're doing it. And the only information that we need to maintain about structure is which maximal projections have reached their final position and which ones have not. Okay, so let's do that here. So again, the derivation tree on the left is going to stay the same, whereas the derivation, so maybe this derivation tree is going to stay the same, but this one is going to be changing. Okay, that's just so that you can keep track of what the original derivation tree looked like and what's going on. Okay, so we just need to keep track of the strings. So will, laugh, every, and boy. What are those strings? Well, they're just will, laugh, every, and boy. Okay. What about the result of putting every and boy together? Well, that's just every and boy. The boy isn't moving, so we can just forget all of the internal structure. That is going to be pronounced as every boy. What about laugh, every boy? Well, here we have to remember that every boy, even though we have forgotten its structure, is something that's going to continue to move. So we keep its string separate. What about merging will with that? Well, will just concatenates directly with laugh, and every boy is still waiting in the wings to move. And when we apply movement, every boy finds its final landing position. There are no more moving pieces. Okay? We've constructed the form, we've interpreted the derivation by interpreting each step as instructions to assemble pronounced strings. Okay. So this is an idea that has been around for a while. So in Survive Minimalism, Thomas Stroik, there's an idea that's similar to this, and in Borsiewski's non-transformational derivations, I read the same idea. Okay, neither of these are very precise. They're not like Jens Michaelis's work, but Jens had the advantage of having a precise formal system of minimalist grammars to work with. But this is an idea that actual linguists have had. And it turns out that the linguists that have had this idea have, in some sense, been deeply insightful about the way the minimalist system works. Okay? Now, what about meanings? Well, again here, interface objects are sequences of lambda terms. Okay? Meaning interface objects are sequences of lambda terms. String interface objects are sequences of strings. And categories to verify whether or not a derivation is well formed are also sequences of feature bundles. In some very, very deep sense, minimalist grammars are manipulating sequences of objects. Okay? So the fact that we're using sequences of lambda terms as representations of meaning objects is just what you would expect if you knew about the minimalist grammar formalism. Okay? Instead of writing sequences, I have a different notation I'd like to use. I'm going to write the first element of the sequence. I'm going to separate from the others by means of a turnstile and write it on the right. It's just notation. There's some other stuff going on too, but I'm not going to discuss it so much here. That's for a different video. Okay, so what we're going to do is we're going to start out by replacing each lexical item by its meaning. Perhaps a better thing to do is to say, in order to derive the meaning of this derivation, I'm going to carry out these operations, but only at the levels of meanings. So when it says I select a lexical item, I'm just going to select its meaning. So I do that here. Here the meanings are capital, are the words written in capitals. Okay, so every boy, I'm going to merge them together. Every is the function, boy is its argument. Laugh, I'm going to merge it together with every boy. But every boy is not done moving, so I'm going to put it to the left of this turnstile. And instead, I'm just going to merge laugh with a variable that is linked with every boy. Okay. Now I want to merge that with will. Well, that just goes on laugh on the head here. And I want to apply movement here. Ah, great. I'm going to take that every boy and combine it with the rest of the clause. Okay. This is how the interface maps work. This was too quick to understand. I'm just presenting you a very quick sketch. The important thing to note is that the interface maps can be defined over the derivations themselves, and the interface maps are manipulating sequences of objects. Just as grammatical formalist checking is manipulating sequences of feature bundles. Minimalism manipulates sequences of objects. From a linguistic perspective, we would say that this description of the interface maps is doing spell out at every derivational step. Okay? You might say that every step is a phase. I don't like using that terminology because, in my opinion, the word phase is overloaded in various ways. There are various different proposals that have the same name, and as far as I can tell, no one has agreed on what phases should be at all. They're really just used as sort of a cover term, and they're a cover term that is somehow related to spell out. So here, because every step is interpreted directly as an interface object, every step is, we're doing spell out at every step. Okay, thank you for listening.